For homework 2, part C, we're trying to find out how far does water encroach into a steel diving bell with known materials and dimensional properties and a known depth underwater. A diving bell typically gets pushed underwater and it's filled with air, so as it gets deeper and deeper underwater, that air experiences more pressure from the water, so it compresses, allowing the water to encroach into the bell. But to start us off, we're going to start with drawing again. So you have your top of water here. Let's just draw a little cylinder down here. And so we're going to have a known depth of D right here. Our material properties of our diving bell, which aren't needed right now, but we'll need them when we do the coding portion of this homework. So we have the height of our diving bell, we have the radius, we have a thickness, which is T, and we have a density, which is rho S, a density of steel. There will also be water within the bell, so that'll be like this little bit here, and then we'll call that Z, which is what we're solving for. So to start, we're going to have a couple different, two equations. We're going to be finding a force balance and a pressure balance, and then these two equations will be plugged in to our computer to code to get actual values for, because they'll be very difficult to solve on our own. So our forces should equal 0, and our pressure should also be equivalent. But if we want to start with a force balance, we'll start here. So we know that F equals ma. So we'll have the mass of the bell times the acceleration due to gravity plus the mass of air, also times the acceleration of gravity. These are pushing the bell up, so it's going to be equivalent to that of the force of the water, which will be water times acceleration due to gravity. But we need to take this equation and put it in terms of the variables that we have for our problem. So if we start with the mass, we know that density equals mass over volume, and it's an effective density because the bell is underwater. So we'll just represent that as rho E, which will go like that. But our mass is going to be equivalent to our effective density, which is rho E times the volume of the bell, times G, which is gravity. And then we're going to have the mass of the air, which will depend on density. But our density of air is going to change, and it's going to be our ideal gas law. So we'll write rho air is equivalent to PM over RT. So we'll plug this in for now for the density, so if it's density of air, it would be PM over RT times the volume of air times G. That's because our density times volume is our mass. And then you have to do our mass of water, which is going to be displaced. But our mass of water would be very similar. Density of water times volume of water times gravity. But then we want to simplify this PM over RT portion. But we know that P, we'll just write it right here, P equals density of water times G times H, which was found previously or in past videos. So the pressure at the bottom must be equal to the pressure of the air, where it's rho WGH, but H is actually going to be our depth down. Or we have a height, but our H is going to be our depth minus that little portion of water in the bell, so it's actually going to be D minus Z. So and then so then this all becomes rho W G times D minus Z over RT, and then our volume of air, I'll write that down here, is going to be equivalent to the cross-sectional area times the height of the cylinder, which is going to be A H minus Z, because remember there's water in the bottom of the bell, so it's going to change the height a little bit. And then of course you have G, so we'll rewrite the left side here. You have rho E times V bell times G plus, I need to fix that. I'll fix it right now. Times rho W times G times D minus Z, which is our p-value, times N over RT, because don't forget the rest of the density of air, times our volume of air, which is A times H minus Z, and then times G equals, and we're going to work on expanding this right side of the equation. So our density of water density of water and volume of water is equal to the air inside plus the volume of the diving bell. So it would be V air plus V bell, but V air is equal to this, which we already have stated. But V bell isn't needed because we are using the effective density, so we're already subtracting this term on the side, so our expression changes a little bit, but not a bunch. So then on the right side we get rho water times the volume, which is A times H minus Z times G. So that is our expression for the force balance. And then to do the pressure balance, as previously stated, we said that our depth pressure is, I'll just rewrite it, is equal to rho GH. And we need an expression to show that P air equals P water. So if we have this expression, we'll make it PW, which needs to be equal to P air. And then we're going to use our ideal gas law, which is PV is equal to nRT. I don't know why I wrote it like that. PV equals nRT. Even though the air compresses, the volume changes, so then our expression would become P equals nRT over V. Excuse me. So if we're thinking about how the pressure changes from the surface of the water before the bell is submerged and then the pressure at the bottom, we're going to have an initial state of pressure and a final state, but our initial state I'll call P naught, which is going to be equal to nRT over A times H, because that's our volume initially. And then our final state, which is just P, we can call PF, P final, is going to be equal to nRT over A times H minus Z. And it's H minus Z because that's our height change with the water in our bell. And so then from there, what we want to do is we're going to write both of these expressions in terms of nRT because it'll be easier to combine them, simplify them, all of that. So this one would become nRT equals PO times A times H, and then this one would become nRT equals PF times A times H minus Z, which then these two expressions can be set equal to each other. So you're left with PO AH equals PF A times H minus Z, and your A's can cancel out. Those cancel out, but we also know that our final state of pressure is rho GH, but our H value for that is D minus Z. So I canceled out these a little early, but you don't need them, so it's fine. So then you're left with PO times H equals your PF, which I think I called it PW up here, but let's consider this as your P final. So it equals rho G, and your H value is D minus Z. We'll note that up here. Rho G times D minus Z, and then times H minus Z, because remember your A's are canceled out. So then our pressure balance equation, the final one is P naught 8 times H equals rho the water G D minus Z times H minus Z. So that's our final pressure balance equation. And then we're going to take both of these and plug them into